In this lecture, we're going to talk about mixed strategy Nash equilibrium, which is arguably one of the most difficult topics that we're going to learn in this course. Now, before I talk about this, let me kind of go back a little bit. Some times ago in lecture 7, we talked about Nash equilibrium, which is kind of like the equilibrium state of the game, which in theory is going to be the state of the game that the players end up with. And we also talked about the saddle point, max min and min max, that kind of thing. And we also kind of see how there could be an example where there is no saddle point, and then this game will stuck in a loop. So Alice and Bob keep kind of changing her mind. So we could not find pure strategy Nash equilibrium for this game. While the last lecture, we also introduced the concept of mixed strategy. So you can kind of see how this will come into play and kind of fix the situation that we get that we stuck in a loop that we see earlier. Now for a little bit of terminology, so a Nash equilibrium, so this definition is basically the same definition that we have seen earlier, except that the strategy that we have here, this is now going to be mixed strategy. It's going to be mixed strategy now. And a little bit of history here. So von Neumann, so this is one of the founding fathers of game theory. He actually proved quite a long time ago, well, this is like 1928, that in any finite 2% zero-sum game, the min-max and the max-min value are going to be equal. So he kind of used the OR, operation research, to prove that these are the do-all thing. However, it was not until 1950 where Nash laid the foundation of Nash equilibrium and proved a more general result. And he actually won a Nobel Prize from basically this theorem. So what he kind of does is that he actually asks the right question so that he can find the answer. You see, when von Neumann kind of proved this statement, so he wasn't sure how the game can be played if there is more than 2 players, like if there are, for example, 3 players. Or if the game is not zero-sum, then what's gonna happen? Are they gonna cooperate, or how are they gonna cooperate, and what's gonna happen in this case? So John Nash asked the right question that, well, maybe what really happened doesn't matter. What matters is how it's gonna end up, and it will end up in an equilibrium. So he kind of proved a general statement where the game doesn't have to be 2%, it doesn't have to be zero-sum. Or in general, every finite game is gonna now have a Nash equilibrium.